Good morning, students. In previous video we discussed hybridization and types of hybridization. Now we are going to discuss about hybridization in organic compounds. Organic compounds means carbon compounds. Before that we had to learn some points regarding carbon compounds, regarding carbon. That is, if every time carbon forms 4 bonds, we know that very well. If carbon forms 4 single bonds with other atoms, if carbon forms 4 single bonds with other atoms, then that carbon undergoes sp3 hybridization. This is very important point. If carbon forms 1 pi bond out of 4 bonds, if carbon forms 1 pi bond, nothing but double bond, then that carbon undergoes sp2 hybridization. If carbon forms triple bond, nothing but 2 pi bonds, or are double bonds like this one, 2 double bonds, one is this one, another one is this one, then that carbon undergoes sp hybridization. I repeat the points once again, listen carefully. If carbon forms all single bonds, that carbon undergoes sp3. If carbon forms 1 pi bond, that carbon undergoes sp2. If carbon forms triple bond or 2 pi bonds, then that carbon undergoes sp hybridization. These are very, very important points. Number of hybrid orbitals in given organic compound is equal to sum of hybrid orbitals of all atoms. Number of hybrid orbitals in a given compound is equal to sum of hybrid orbitals of all atoms. Then one more point. Number of pure orbitals. Pure orbitals means the orbitals which are not involved in hybridization is called pure orbitals. Those are also called unhybridized orbitals. Unhybrid orbitals or unhybridized orbital. Number of unhybridized orbitals is equal to number of hydrogen atoms plus 2 into number of pi bonds. Number of hybrid orbitals equal to sum of hybrid orbitals of all atoms. Number of pure orbitals equal to number of hydrogen atoms plus 2 into number of pi bonds. So these are the formulas to calculate number of hybrid orbitals and the number of pure orbitals in a given organic compound. If you see the example, then you will get clear idea about this one. See, in this case CH3, CH3. In this case, before that we have to draw the structure. What is the structure for CH3, CH3? CH3, C single bond, H, H, H bond, C again single bond hydrogen, single bond hydrogen, single bond hydrogen. If you observe this structure, carbon forms only single bonds. It couldn't form pi bond. So this carbon undergoes which hybridization? sp3 hybridization. This carbon also undergoes which hybridization? sp3 hybridization. If carbon undergoes sp3 hybridization, then how many hybrid orbitals are formed here? 4. Here also 4, because sp3, 4 orbitals will form. We know that very well. 4 plus 4, how much? 8. What these 8? These are hybrid orbitals. Then what about pure orbitals? Nothing but unhybridized orbitals. What is the formula? Number of hydrogens plus 2 into number of pi bonds. In this case, number of hydrogens how much? 6. Plus pi bonds how much? 0. 6 plus 0 how much? 6. So pure orbitals are how much? 6. Hybrid orbitals are 8. Sometimes you may get the question, what is the ratio of number of hybrid orbitals and pure orbitals, or what is the ratio of number of pure orbitals and hybrid orbitals. Sometimes you may get such type of questions also. Like that we can solve hybrid orbitals and pure orbitals in a given organic compound. One more example. See, CH3, CH2, CH3. First what we have to do, we have to draw the structure for them. CH3, CH2, CH3. This is the given compound. What is the structure for this? C, H, H, H. Already we knew how to draw the structure for a given organic compound. So we have learnt all these things in class 10 chemistry. So this is the structure for this compound. In this structure also there is no pi bond. Then all carbon undergoes which hybridization? sp3. All undergoes sp3 hybridization. So 3 sp3, nothing but 3 into 4 orbitals, total 12 orbitals. These 12 orbitals are what? Hybrid orbitals. Then what about the number of pure orbitals? Number of hydrogens plus 2 into pi bonds. How many number of hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. 8 plus pi bonds 0. Total 8. These are what? Pure orbitals. Next one more example. CH3, CH double bond, CH2. In this case, this carbon undergoes sp3. This carbon also undergoes this carbon here. It forms double bond. So this carbon undergoes sp2. Here this carbon also forms double bond. So this carbon also sp2. Then how many hybrid orbitals? If it undergoes sp3, 4. But if it undergoes sp2, it forms 3. Here 3, here also 3. 4 plus 3 plus 3. Total 10 hybrid orbitals. Then what about pure orbitals? Pure orbitals formula is what? Number of hydrogens. How much? 3 plus 1 plus 2, 6 plus 2 into number of pi bonds, 1. Total 8. In this case, this carbon forms single bond, so this carbon undergoes sp3. Here this carbon forms double bond, so that it undergoes sp2. Here this carbon also forms double bond, so that this carbon also undergoes sp2. But this carbon forms only single bond, so that this carbon undergoes sp3. Here 4, 3, 3, 4. Total 8 plus 6, 14. Pure orbitals how much? Pure orbitals formula, number of hydrogens plus number of 2 into pi bonds. 2 into number of pi bonds. Total 3 plus 3, 6. 6 plus 1, 7. 7 plus 2, 9. Sorry, 3, here 2 is not come. 2 didn't come here. 3 plus 3, 6 plus 1 plus 1. Total 8. 8 plus 2 into how many pi bonds? 1. Total 10. Next one, benzene. In benzene molecular formula what? C6H6. This is structural formula. If you see the structural formula, each carbon forms double bond. That means each carbon undergoes sp2. That means how many hybrid orbitals? 6 into 3, how much? 18. Pure orbitals how much? Pure orbitals formula is what? Number of hydrogens, that is 6 plus 2 into number of pi bonds, that is 2 into 3. Total 12. So 12 is the number of pure orbitals, 18 is the number of hybrid orbitals. Sometimes you may get this type of compounds. That means this is called bond line formula. Bond line formula means only bonds are present, atoms are not visible. In such cases, first we have to draw the structures based on the compounds. Then we can find hybridization. Automatically we can find number of hybrid orbitals and pure orbitals. So this is the way to calculate number of hybrid orbitals and number of pure orbitals in a given organic compound. Next important topic in this chapter is VSEPR theory. VSEPR theory means valency shell electron pair repulsion theory. Valency shell electron pair repulsion theory. Postulates. According to this theory, the shape of the molecules depends on electron pairs of central atom. In every molecule, central atom is present. In that central atom, lone pairs and bond pairs are present. Those lone pairs and bond pairs are collectively known as electron pairs. I repeat that point once again. Listen carefully. In every molecule, central atom is present. In central atom, lone pairs and bond pairs both are present. Those are collectively known as electron pairs. So what this theory says? The shape of the molecule depends on electron pairs, nothing but lone pairs and bond pairs of central atom. That is the first point. That is the meaning of that point. Second point, lone pairs occupy more space than bond pairs around central atom because lone pair belongs to one atom and bond pairs belongs to two atoms. This is also one of the important point. See, I will show the example, then you will get some idea. For example, I take He2O. This is formula for molecular formula for what? Water. In that molecular formula, oxygen is the central atom. In that oxygen, what is the atomic number? 8. What is its electronic configuration? 1s2, 2s2, 2p4. This is orbital representation. If you observe this orbital representation, it contains 2 unpaired electrons and 2 lone pair of electrons in outermost orbit. This is outermost orbit. This 2s2 2p4 is present in outermost orbit of oxygen. So this oxygen contains 2 lone pair of electrons and 2 unpaired electrons. So what is the point here? This oxygen forms 2 bonds with 2 hydrogen atoms like this. And also it contains 2 lone pair of electrons. See, these bonds are formed by overlapping of p orbital of oxygen and s orbital of hydrogen. Here also p orbital of oxygen and s orbital of hydrogen. So what is the point here? This bond contains electrons. 2 electrons. These are what? Bond pairs, because they form bonds. But these are lone pairs. Why these are called lone pairs? They don't involve in bonding. What is the point here? These lone pair of electrons belongs to one atom, but these bond pairs belongs to 2 atoms. See, the electrons which are present in bond is called bond pairs. These bond pairs belongs to, the electrons which are present in this bond belongs to hydrogen as well as oxygen. Here also the electrons which are present in this bond belongs to hydrogen as well as oxygen. So what is the point here? Lone pairs belongs to one atom, bond pairs belongs to 2 atoms, so that lone pairs occupy more space than bond pairs in any molecule. Next point. Lone pair causes more repulsions than bond pairs. Lone pair causes more repulsions than bond pairs. That means compared to bond pairs, lone pairs causes more repulsions. So lone pair repulsions are more than lone pair bond pair repulsions, which are more than bond pair repulsions. That means between any electrons repulsions occur. We know that very well. But those repulsions are more between lone pair and lone pair, which is more than lone pair and bond pair, which is more than bond pair and bond pair. Next. If the number of bonds between 2 atoms increases, then the repulsions between bond pairs also increases. See, for example, take CC sigma single bond. That means between, if sigma, one bond is formed between 2 carbons. Here 2 bonds are formed between 2 carbons. Here 3 bonds are formed between 2 carbons. All these are what? Bond pairs. Just now we discussed it. The electrons which are present in bonds are called bond pairs. If a number of bond pairs increases between 2 atoms, then repulsions increases between those atoms. Automatic repulsions increases. So that is the meaning of that point. If number of bond pairs increases between 2 atoms increases, automatically repulsions also increases. So these are the postulates of VSEPR theory.